Okay, we're going to do something with the conic sections today, conic sections, and we'll discuss 3 different types. First will be the parabola, and the parabola is formed if you take a line and fix a point, and then take a set of any other points whose distance from this point, this fixed point, to this line is the same. So it's a set of all of those points. So the distances in here are the same. In other words, this is D1, this is D1, this is D2, this is D2, D3, D3. Okay, so that, if you form all those together, that gives you this type, this shape of curve. That's what you're going to see. Okay, now it turns out that this distance right in here is special. In here, we can call this P in here, and this is also P. Same distance from here to here as from here to here. Okay, those would be the same because that's by definition. But since this is where the focus is actually perpendicular to the line that I've drawn here, which by the name has it has a name called directrix. Okay, so that's what forms a parabola. Now, these things can be rotated or turned sideways or turned upside down, whatever it might be. We're going to focus on vertical and horizontal parabolas in this section. So this is our standard form that we have right now. This is a directrix. Vertex is that point here, right at the very, in this case, the very bottom of the curve. Vertex right there. It's on that line that's perpendicular from the focus to the directrix. That is your vertex, and we have what's called a vertical axis for every one of these parabolas, and it's a line again that runs right through here. That's called the axis. Okay, now the axis will be vertical if we have this form for our equation, and it'll be horizontal if you have that form. So we have a vertical parabola here. And let's see, now the P, again, the P is that number that I've mentioned over here. This is the same P as in here, same number. Okay, the parameter P. All right, now a couple things. If P is a real number, if it's less than 0, then the parabola is going to go downward like this. This is for P less than 0. If P is greater than 0, it'll come up this way. Or if it's on left right, this is P positive, and this would be P negative. Okay, so depending on if it's vertical or horizontal. Okay, and there's one other topic, one other concept associated with this parabola, and that is, in fact, I'll show you that when we get to it in this problem here, once we have a little bit of a sketch in front of us. Okay, so here's a typical problem. Let's find the vertex, and we want the vertex, the focus, and the directrix for this parabola here. So let's work on that. Now, first of all, let's get it into our standard form. See if x squared can be equal to negative 6y. Now that tells us in here, remember our form up here looks like this. This is the form we're working with here. And the number right in front of the, in this case, the y term is a -6. So that is our 4p. That tells us what p is going to be. Okay, so this will be -3 over 2 is equal to p. So that tells us a couple things. Let's put that together with our. We can see that our vertex must be 0, 0, because we have this form here, and you can see that the h must be 0 and the k must be 0 in order for it to transform to this. Okay, so those are the values that are implied by the h and the k. So this is the h and this is the k. They're zeros in our given equation. Okay, now let's start drawing this thing over here. I'm going to use, see, I'll use this red one here. Oops, I'll use a red one. Okay, so here is the vertex. And now because this p is negative, you know this thing's going to open down. Opens down. And the distance from the vertex to the focus is going to be 3/2, but it's down this way. So it'll be right there. Okay, so that is your focus. I'll just label it with an F. That's the fixed point where all this stuff began. Now, we can find our directrix because we know that it's equidistant along this line. This is our axis of symmetry. Okay, axis of symmetry. It's equidistant from that focus to the directrix. So the directrix is going to look like this also. 1.5 units away from the vertex. Same distance as the focus is to the vertex. That's V. So here's our directrix. And we can easily see from our drawing that line is 3/2. Okay. It lies 3/2. Okay. Now let's put in, we're going to have to put a few points in this. Now just to get a little more accuracy, this is where the lattice rectum comes in. Okay, lattice rectum. It is one of the focal chords. Focal chord is a line that passes through the focus and has endpoints on the parabola. So, for example, let's say this were my parabola and here's the focus. That's a focal chord. Goes through it like that. Here's another one. Okay. Now the lattice rectum is the one that runs through it and is perpendicular to the axis of symmetry. Okay, so you say it's parallel to the directrix. Okay, but it's perpendicular to the axis of symmetry. That right in there, that focal chord, that's the lattice rectum. Okay, and what's unique about it is that it has a length equal to the absolute value of 4p. So we can see in here that the 4p is a -6. So absolute value of 4p is a 6. So the distance across here is 6 units. So if I can measure here 3 units on either side, I automatically have 2 points on that parabola. Now, I could have found a couple points just by substituting in some x coordinate, an x value, and solving this for y. I mean, that wouldn't have been a big deal, but I wanted to illustrate this concept of the lattice rectum. It can help you find a couple fast points for your parabola. Now, let's go ahead and connect those points through this way. And now, without getting more points, this kind of gives me the feel of the curve. But you know, if you wanted a little more accuracy, then you would have to pick an x coordinate, an x value, say out here, and then get the corresponding y value. That would give you a little more accuracy. But as long as you got these 3 points and you got the focus located here, here's your directrix, and you can see that focus is 0, -3/2. Those are the coordinates of it. your vertex is 0, 0. So that's enough on the drawing. Okay, okay, got another one here. See if I can make that a little bigger. Oh, all right. Okay, so that's pretty big. Let's see. Okay, that should be enough room. Okay. All right, so we're gonna do the same thing with this one. We're gonna identify the vertex and focus and the directrix, and then do a graph of this thing. So let's go ahead and put it into standard form. Okay, so now I see my y is being squared here, so I'll keep that over here, and I'll put the x term on the other side. Now, in order to get that form, this is what we want. We want y minus k squared equals 4p x minus h. That's what we want. So I need to complete the square on this guy over here. So I'm going to add 2 squared, right? And over here, add a 2 squared. That makes this y minus 2 quantity squared. And this, I'm going to write this as 4 times x plus 1. Okay, so in this form, you can see now that the 4 equals 4p in here. Okay, the 4 is a 4p. So that just tells us that p is a 1. Okay, now vertex is also apparent from the standard form also. Vertex, you can see is over here. Notice we have a -1 for the h and 2 for the k. So remember, this is in form x minus -1. So it has to be in that form x minus the number, the parameter itself. So the parameter we can see must be the h value is actually -1. Okay, so here's our vertex. Now, it could probably construct more information from this, but let's just go right over to the graph and see what we can put on here. So -1, 2 is a vertex. So I'm at -1 up at 2. So that would put me about right here. Okay, -1, 2, that's the vertex. And notice this is a sideways parabola because the y is being squared. So it's going to open left or right. In this case, since p is positive, it's going to open to the right. So this fact that p is greater than 0, and the fact that we're talking about a y squared term, these two together tell us that it will open right. Okay, so that means now my directrix, this p equals 1 tells me the directrix will be 1 unit, in this case to the left of that vertex, and the focus is 1 unit to the right. And this would be, so this is the directrix. And we can see its equation must be x equals -2. We can see that. And the axis of symmetry comes through here. And again, you've got the 2 points here. There's your focus, and here's your vertex here. Okay. And that means let's look at our last rectum now. It's comes in here. It tells us, this tells you that that length, which is called LR, is 4. So along here, I just need to go up 2 units, down 2 units. That's on the focal chord. And that gives me my 2 ordered pairs there. Now you can confirm that those are correct. If x is 0 in my original equation, well, let's see, if x is 0, then we get y equals, let's just do that. Then we get y squared minus 4y equals 0. So we have y times y minus 4. So we get y equals 0 and y equals 4 as coordinate values when x is 0. And that's consistent with what we have here. We've got a 0 and we have 4 for the y's. Anyway, let's connect them. It's going to come out like that and something like this. Okay, with just those 2 points. I'm not showing anything else. Okay, so we've got everything under control there. Now, if you want to list, we got the vertex here. We got our focus. You can see the coordinates there. We've got 0, 2 on that focus. And that's all we need. So we have our standard form, vertex, focus, and we have our directions up here. Okay. All right, we're going to try one more of these. Okay, this time we have the vertex and focus given to us, and we want to find an equation. Okay, well, okay, just to get your bearings straight, you'll notice that vertex is negative 2, 1, and the focus has the same x coordinates. So it means that they're both running along the same vertical line. Okay, so, well, anyway, but this will help you to get your bearings. So it's negative 2, 1 is over here. Okay, negative 2, 1. And negative 2, negative 1 is down here. Okay, so that's the focus and that's the vertex. That means your axis of symmetry must be running through vertically this way. So now you can see your orientation of this parabola. So let's make sure we don't get these mixed up. That's your vertex and that's your focus. Okay. Now from there, you can see along that axis that the distance from the vertex to the focus. Okay, that is, according to this, it looks like 2 units. Okay, so we can see from the diagram that P actually equals, in this case, it would have to be a negative 2 because the vertex is up here, focus is down here, it's opening downward like that. So P must be negative and it's the same value as the distance between these two. And from our diagram, from our sketch here, we can see that the distance between there is 2 units and it's a negative. So that tells us now a lot about our equation because our equation it's going downwards. So we're going to have x, let's see, plus a 2, okay, equals negative 4, whoops, negative 4 times that 2. Okay, so I've got a negative in there for the P. I've accounted for it. And then I have, of course, y minus 1, like so. So just one more step to rewrite. Got negative 8 y minus 1. And that's probably the handiest way to leave your answer like that. You don't want to expand it or anything. This is a standard form. Okay. And it doesn't say to graph it, but we can see that our LR, the length of the lattice rectum, okay, is going to be 8. And that means in here we've got 4 units this way. Oops, come on, 4. I can't hang there too long or else it wants to do things. Okay, and 4 that way. And we can get a nice little sketch coming through like that. Okay, And of course, I didn't draw the directrix, but you know it's another 2 units up this way, so it'll be right along here, coming that way. Okay, 2 units away from the vertex, just as the focus was 2 units away from the vertex. So this is directrix. And you can see that that equation will be y equals, what is that, 3, right? Okay. All right, now we've got the ellipse to talk about. Now the ellipse is a little different. Here's the description of your ellipse based on these points, these sets of points, just as in the last one. So the ellipse is the set of all points, the sum of whose distances from two distinct fixed points, foci, is constant. Okay. So what we're seeing is something like this. I'll put a little sketch over here. You have 2 points, and these are we'll call this F1 and F2. And if you take a defined length, let's call it D. Okay, let's call it D. Oops. And you connect it to these 2 points like that. Oops. And you keep that connection constant. In other words, whatever this is, let's say this is D1 and this is D2. That's sum D1 plus D2. There's always a constant, we'll say D. If you do that, you will form, if we just put all these together now, you will form an ellipse. It will look something like this. Okay. Now that's solid in there. Okay, so it's a kind of a crude thing. And now mostly when we look at an ellipse, we see these points here on the end. And some would argue that these 2 are important up here also, this one and this one. But these 2 here that lie along along this line that connects the 2 foci together, these 2 are called vertices. We'll call V1 and V2. Or we'll say V2 and V1, just to be consistent with F1 and F2. So they're called vertices, and they're on the ends here. Okay, the center is right here where you would think it would be. And this axis along here, this is called the major axis. Okay, the length of that major axis is, well, the distance between the center and the foci is A. So this distance from here, that's A. So the length of the major axis is 2A. The distance in here, I'm going to try not to muddy this up in here with too much. That distance is B. And that, well, this line that comes through here, it's called the minor axis. Comes all the way through here. And that's called the minor axis. Okay. Now, through a little bit of logical reasoning, we also give a name to this. We have to give this a name. We're going to call this C, the distance from the center out to the focus. That distance is C. Now, it turns out that there's a nice relationship in here it's not obvious until you mess with these, until you move that point around, and then you'll notice a few things occur because of the Pythagorean theorem. A few things occur, and because of the nature of the way this was defined. Because of the Pythagorean theorem, you're going to see a relationship between this B, this C, and the distance across here from that point up on top down to the focus here, the diagonal. It turns out that that length actually is going to be A. Okay. Um, A, like that. And we have this relationship that B squared plus C squared equals A squared. Now this is better known, better remembered this way. C squared equals A squared minus B squared. This is the one that we remember about this. And remember, what I'm saying is this, I haven't shown this, but this is B, definitely this is C. And it turns out that that length along here from this point to this point is going to be an A. There's a little bit of argument that goes with that. Remember, this is 2. This length here, A, another A, that's 2A. If you were to run this point all the way down here, let's say you ran this point. In fact, let's just run it back this way. If you stopped right here, oops, you know what? I'll take a chance with this. Put a little nice little dot here. If you stop there, then the length. Okay, I'll make it blue. Then this length in here kind of, if you're going from here all the way to here, remains the same. Remains the same. It doesn't change. You still have that distance along there, d1 plus d2. Now, if it's up in here, okay, this was getting a little bit messy over here. So in trying to explain why is it diagonal A over here, why is it A? So I thought I'd give you a little more insight into that. This diagonal in here, why is that A? Well, okay, here's one argument. Down in here. Beginning here, let's look at this first, right here. Okay, this is the length. This is the focus. So there's a vertex here, and here's another vertex on this end. And here's the center. Okay, and the distance from center, this is the center, so a focus is C. Okay, so now you have to imagine that this D1 plus D2 has been collapsed on itself, and it's measuring across here and then back this way. So it's coming across, stretched all the way from here this way, and then it still has a little bit more to go because it has to come back to the other focus. So that's that D1 plus D2 in there. So right now the D2 is the yellow and the D1 is the blue. D1 is the yellow along this way, and the D2 collapsed over here. Okay, so in any case, the lengths here, what they amount to are these numbers in here. The length, D1 plus D2, the whole length of yellow plus the blue is up here. And it's equal to C plus this C in here plus another C plus this other number in here, which is A minus C. So that gives you the full yellow. Then you come back with the blue, another A minus C. So D1 plus D2, when you add these all together, you just get 2A. Okay, well, now that's a relationship that holds for whatever size D1 and D2 are. They're equal to 2A. So it's actually equal to the length of the major axis. Now, that tells you a couple things. Number one, if this positioning here were to be, that D1, D2 were to move, so that point became here, and you just had this and this together now. You can see we've got in that position, you have an isosceles triangle, and D1 equals D2. So you have this statement down here, D1 equals D2. That means they're the same size, so that tells you that D1 and D2 are both equal to A. So that diagonal from here to here is an A, and that's where your relationship comes from here. So it's not magic, and it's not arbitrary either. It is according to the way these were dimensioned in here. It rises naturally out of that. So, all right. So let's continue then. Okay, and now with a little bit of work, we can show using a distance formula. By the way, that's show any of that, but it is it results out of the distance formula. Setting up the distance formula between these points, a point out here, x, y, and these 2 points here on the two foci. You can set up a distance formula relationship, and then through quite a bit of tedious algebra, you can arrive at this. Well, you can generate it for the center at the origin, and then just from that point you can translate your center in x direction and y direction to arrive at this one here. So I left that. I'm not going to go into all that detail for here, but it is based on the distance formula and some tedious algebra. So okay, let's see. I think that's enough about this for now. Let's do an example. Let's get into a little. Okay, we're going to do a couple of examples here. Let's see. Okay, so we have. Okay, we're going to work on this one here. So first of all, you get it put in the standard form. So that means we need a 1 over here. So we'll divide everything by 63 to get this set up here. So we'll get a 1 like that. This will translate or simplify to a 21. And this is a 9. Okay, so from here, you could see that the A is A squared is a 21, which is bigger than the B squared, which is only a 9. So this tells you that the major axis, in this case, it actually lies on the x-axis, because we can also see that our vertex, see that right away, our vertex is at the origin for this one. So here it is, vertex at the origin, and I'm sorry, not vertex. I meant center. Center at the origin. Now this tells you that A is root 21 and B is a 3. Okay, so when we put our vertices on here. We're going to have A's for 21, which is, what's it about? 4.6? I think it's about 4.6. It's about 4.6. So when we come in here to get the sketch in here, we come in here, we're about there. I gotta be quick on this. Doesn't like me to wait. There's another one there. So we got a vertex here and a vertex here. You can say 1 and 2. Okay. Now these are the co-vertices are the ones that on the minor axis, and they are, we can see that 3 units above. So you got one here and one down here. Those are the co-vertices. So we now just try to connect smoothly, and there is your ellipse. Now, the only thing that I didn't put on here were the, and we can list, of course, the vertices. In this case, easy to just write plus or minus 3, 0. And you can say the CV, the co-vertices. Oops, I'm sorry. That was the co-vertices. The vertex. Oops. The vertices. They would be at the plus or minus 21, 0. And the co-vertices, see, I got that backwards now. I tried to just save a little time. Okay, so let's fix that. Co-vertices, they would be at 0, plus or minus 3. Sorry about that. Okay, and the only thing missing are the foci. Okay, and we would use our relationship that the c squared equals a squared minus b squared. Okay, so we put these in. Let's see, we would have a 21 minus 9. So c is the square root of, what is that, 12? So it'd be 2 root 3. So our foci will then be at plus or minus 2 root 3, 0. Okay. Now let's take this next one down here. Okay, we don't have a lot of room, but we'll see what we can do here. Let's start up here. First of all, you got to put it into standard form, so it's going to require completing the square. So let's write it this way: 9x squared plus the 36x, and then I'll leave some room here. 4y squared minus 24y, and then I'm going to put that 36 on the other side as a negative. Okay, so this is what I would suggest. Take out that 9. This will be a 4x. And left extra room in here. And take out this 4 here. And I'll leave some room there. Okay, because now I'm going to complete the square here. Take half of that 4, make it a 2, add it after I square it. So this will be 9x squared plus 4x plus 2 squared. And a 4 times a y squared minus 6y plus 3 squared. Now, what happened on the right side? We had a negative 36. Over here, we had 9 times 4. So I got to add a 36. And over here, I had 4 times 9. I add another 36 to keep it balanced. This side becomes x plus 2, quantity squared. And a 4 times a y minus 3, quantity squared. And this simplifies on the right side to just 36. Okay, almost done. Divide by that 36 to get the 1. So you'll have this. And this will reduce to x plus 2 squared over 4. And this will be y minus 3 squared over 9. So now you can see what we have in front of us. we've got major along the y. We can see that our a squared is a 9, so a equals 3. And our b squared is a 4, so b is a 2. Our center is at -2, 3. And that's enough to get the sketch. So let's do a quick sketch of this one. -2, 3 would be about here. And let's see, 3 in the y direction. So that would put us up about here and down here. That's the major axis along there. From that point up there, vertex 1 and vertex 2. And then B is 2, so the co-vertices would be 2 units, one over here, away from that center, and another one over here. And from there, you can easily spot what the coordinates are. And we'll also do a little sketch. Okay, a little bit wonky there, but okay, so you can see your vertices and let's see, we've got -2 plus or minus. Oh, I'm sorry, -2. You have a 0 and -2 with a, it looks like a 2, 4, that's a 6, right? -2, 6. And your foci, well, we don't know what those are yet. We have to compute. But you know c squared is a squared minus b squared. So we'd have a 9 minus 4. So c is the square root of 5. Okay, so your foci would be at that -2, comma, root 5. Oh, hold on. It's not root 5. I gotta be careful with that. It's 1, 2, 3 plus or minus root 5, because you're measuring c off of the center of the ellipse. So you start with that center and then you add out or you subtract down to get to this, to the foci. Now the vertices, we can also look and say those are measured in a sense from the center. I usually don't when I'm working with a drawing, but you could. In a pinch, you could say the vertices would be in this case at that the value of, was it h in this case, and we'd have k plus or minus a. I usually don't like to do that. It's simpler to just work with the dimensions, knowing that what a represents. It's half of that major axis, starting at the center, and you just work your way from there up or down to get those vertices. But you could also do it like this. Notice in this case, k was a 3, and if you subtract 3, you get the 0. If you add 3, you get the 6. But I usually don't do that. But anyway, did it there. Okay, so we got everything calculated on that one. It's all set.